So today we're going to talk about Big Bang Theory, how our universe began, and all that wonderful stuff. So here we go. This is where a lot of students kind of look at me like, really? This is crazy. But it kind of is. So the Big Bang Theory explains the origin of the universe. Origin means the beginning. So this is where this is as far back as scientists have theorized on our universe. This theory first came around in the 1950s, so it's been around for a pretty long time, and it is the most accepted and supported theory still today. So there have been plenty of scientists that have tried to debunk this and prove it wrong, and they have had no success. So here we go. So the Big Bang Theory begins, move myself. So if you could imagine the very beginning of anything, of the universe, before it existed. The Big Bang Theory states that in the very beginning, all of the energy that is composed of our universe, all of it, was confined down to a tiny, tiny ball of energy. So incredibly hot, incredibly dense, a lot of stuff crammed into one small ball. So if you're wondering, well, where did that ball come from? We don't know. Scientists, the Big Bang Theory begins with the small, tiny ball. It does not explain or even try to explain where the ball of energy comes from. So that's where I suggest maybe your own personal beliefs or religion can come into play, but that's up to you, obviously. But just know the Big Bang Theory is not going to explain where that ball came from. So it starts with a tiny ball, and then about 13.7 billion years ago, because that's how old the universe is, it started to violently expand outward. Now, in the very beginning, when the theory first came out, they said it was a big explosion, hence the Big Bang Theory. But in recent years, scientists are trying to explain that instead of an explosion, it was probably just a violent expansion. Nothing like blew up, that it just started to expand in every direction. So I know this sounds a little nutty, but this is the theory. And there's lots of evidence to support it. We'll go over two of the biggest parts of that evidence. But first, let's talk about how do you get energy into things with mass and matter that will make stars and planets and stuff like that. So that's where Einstein comes into play. So Einstein, with his famous equation, E equals mc squared. So essentially, E is energy, M is mass, and C is the speed of light squared. So it's going faster than the speed of light. So basically, this explains, and this was a lot of his theories, that when energy expands outward, it will naturally cool off. And it would take a while because obviously this is incredibly hot. Once it cools to a certain temperature, energy will turn into matter. So basically, if you can move matter, something with substance like us, if you move us faster than the speed of light, under Einstein's theory, we would turn into energy. We would completely go away and just be energy. And if you slow energy down, it turns it into matter. I know that sounds a bit nutty, but that is Einstein's E equals mc squared. So under the Big Bang Theory, and we know this is true, we can duplicate this in the lab, when the energy that it was expanding from the tiny ball, when it starting to slow down and cool off, that energy turned into the most basic forms of matter. And that would primarily be hydrogen and helium. So that's why, and most of it's actually hydrogen, that's how the main elements that make stars exists in our universe. So lots of hydrogen and some helium in our universe. And so the simple building blocks of stars were made, which would make our first nebulas. Then those nebulas would make stars. Get enough stars made, then they can start to come together through the gravitational pull and make the first galaxies. And there you go. And that would be happening in every part of the universe. So that's how you go from energy to matter. It slows down, it cools off, it turns into matter. And the matter it would turn into is primarily hydrogen. So this chart just kind of explains the illustration of the Big Bang. So you start over here with where it begins, time begins, where that expansion or that inflation occurs, expanding out to the size of an atom in a fraction of a second. And then it's starting to cool off, like number 3, a rapidly cooling cosmos permits quarks to clump into protons and neutrons. So that's how you're getting some of the building blocks that would make the first atoms. And then you've got, as it expands outward and like farther from where the Big Bang originated, then you have electrons combining with protons and neutrons to make the first atoms, mostly hydrogen and helium. Gravity makes hydrogen and helium coalesce to form clouds. That would be your nebulas, where stars would first form. And then you've got your galaxy clusters forming outward, where you would eventually start to see enough stars dying out that would make some of the first planets. So that's essentially the Big Bang. I hope you didn't write any of that down. You didn't need to. That was just a chart. Okay, so this is supporting evidence number 1. Where am I going to put myself? How about right here? So Hubble's law. Hubble did a lot of stuff, in case you can't tell. He was involved in a lot of, obviously, galaxy stuff that you learned about yesterday. But with his research with galaxies, he discovered something. So, and he discovered Hubble's law. We named it in 1920s. That's when he did a lot of his work classifying galaxies. And using a spectroscope, which we talked about before, looking at distant stars and what elements come from that. But we can also tell, using the spectroscope, whether something is coming closer to us or something's going farther away from us. And so he would, while he's looking at galaxies, he would label whether or not they were moving away or towards us. And what he discovered is that all galaxies are moving away from us and from each other. So that expansion idea takes place with Hubble's law. And the standard explanation or analogy for it is the raisin bread dough, which I know sounds kind of nutty. But you've got a dough ball, and you can see the raisins as it's expanding and rising and making it into bread. Those raisins, which are galaxies, are expanding in every single direction, moving farther away. So that's the first supportive evidence, knowing that not only did the Big Bang create the first expansion, but that it's just been going on ever since. It's still expanding. The second supporting evidence is cosmic microwave background radiation. So this you read about briefly in our our electromagnetic spectrum web quest that you guys did. So this was discovered by Arno Penzias and Robert Wilson in 1965. So they had an antenna, which is behind them. It's called a horn antenna. It's just a type. But you listen with it. It's an antenna, right? So you're hearing things using kind of like radio waves, but these are transmitted through microwaves. They discovered faint radiation that was coming from every single direction, no matter where they pointed the antenna. And it was like a static sound. And so no matter where they put it, it was the same. It wasn't louder in some direction. It wasn't softer in another one. Because if there was like some explosion happening or a supernova in one area, you would expect the antenna to pick up more radiation from that area than over here. But that's not what they got. It was the same faint radiation in every single direction. And so essentially what they detected was the cosmic microwave background radiation. Scientists later understood what it was that they found, that it was the leftover thermal energy from the Big Bang. So the Big Bang was so violent and such a large expansion process that the static, that radiation from that Big Bang still exists today in every part of the universe. So that's supportive evidence number 2. So that radiation had to have gotten there from somewhere. So, and you don't have to write this part. I just like to put it in there. So for those of you that are thinking in your head, this sounds crazy, just remember, scientists, just because scientists agree on it doesn't mean it's not questioned. There are plenty of scientists who have made it their life's goal to discredit the Big Bang Theory. And every time they try, it only strengthens it and makes it stronger. Because it's been going on for 60, almost 70 years now, and there's still no success with debunking it. In fact, a lot of the evidence that they think that they've got to debunk it ends up only strengthening it, such as we found gravitational waves that would have been created from the expansion, like think of a ripple in the water expanding out in every direction. We found the gravitational waves from the Big Bang in 2014, which only then just solidified this theory even more. But it could still get debunked. I mean, it's still possible, but there have been plenty of people trying. So last, let's talk about the future. So scientists have 2 possible ideas on what will happen to our universe in the future. The first idea is that the universe will continue to expand forever. Eventually, it will completely all cool and just pretty much exist the way that it is. This is the most popular and most likely theory. There is another theory out there that has been around for a couple decades. It's called the Big Crunch, where expansion will stop and an inward contraction will begin. And when it all contracts back to the same spot, that will make a giant black hole. So there's that idea. I like option 1 better, but the Big Crunch sounds pretty awesome too. So, so there you have it. That's the Big Bang Theory.